Hello and welcome and good afternoon, everyone. My name is Javier Pérez. Xavi, I'm the head of data at CARTO, and today I have the pleasure to share the stage with my colleague, Giulia Carella.
Hello, everyone. I'm Giulia Carella, and as Flo said, I'm a data scientist at CARTO.
What we're going to do today in this session is that we're going to discuss how we can combine multiple sources of location data streams and then showcase 2 examples on how we can use that to make more informed, more optimal business decisions. So location intelligence is changing the way we do business across sectors, and I think this conference is indeed just about that. Besides the fact of the availability of new tools to perform this type of analysis, we see this trend happening for 3 main reasons. First, the availability of new location data sources coming from entities such as telcos, financial institutions, open data portals, that are now more available for a new type of analysis that can uncover all the spatial patterns in this data for optimization and for prediction. And finally, because organizations such as yours are adapting themselves to catch this wave by creating business intelligence units and data science teams. There is a fast-growing amount of data being generated nowadays. We have mobile phones, IoT devices, we have cars, satellites, electronic payments. All this vast amount of data has one key and common component, that is location, because as we like to say a lot in CARTO, that everything happens somewhere. However, we still see a lot of organizations that base their decisions on census data. And I mean, with no doubt, it's one of the most important sources of information, but as you may know, it only gets updated very often. So in order to use census data, you have to project to the present using the latest publication. And with the pass of the years, this projection becomes more outdated and at the end is less accurate for analyzing. These here are the main categories of the location data streams that compose CARTO's data catalog. So as you can see, we have financial data on where people spend, coming from banks or credit card companies. We have human mobility data, so how people move, where people go, from where do they come from, coming from telco and mobile apps. We also have demographics. We have housing information, not only from the cadastre, but also from the real estate market and how is that behaving. And then road traffic, points of interest, and so on. And the key thing here is that being able to use multiple of these sources together comes with certain challenges. And this is what we want to discuss now.
Imagine, for example, that you get only a sample of the data, but this is not actually representative of the true population. And this happens all the time, for example, when you get GPS data from apps on your phone. Everyone has different apps, and the way these apps transmit the signal also differs. Then we can get some data that have this sampling issue, and when you want to use this data, the assumptions is that this sampling is actually irregular, so you can actually use that to represent the whole population. But most of the times this is not actually true, and the sampling introduces some time and space varying biases that you need to account for. The second big challenge that we have to face is with data anonymization. These procedures are actually important because they help us complying with privacy regulations, but this means that we have some gaps in the data. Think, for example, of credit card transactions that you can count in a given area. Most of the times, if the number of merchants is below, for example, a given threshold, these data get anonymized, and you have a gap or a missing data there. The third challenge, and this is a big one, is that most of the times, in order to create meaningful units for analysis, you need to aggregate the data. But the way you do that may differ. For example, you may get data aggregated over grid cells of different sizes, or data aggregated over administrative units. And this, for example, is what you usually get with census data. What you see here are three examples of different aggregations. We have demographics data aggregated over a grid of 100 by 100 meters, financial data aggregated over a grid of 500 by 500 meters, and finally road traffic data aggregated by road segments.
So what's CARTO doing to overcome this challenge? So right now we are working towards the creation of a common reference grid in which to project or aggregate data coming from all these different data sources. So our customers have it way more easier to be able to consume all of them in their spatial models in an homogeneous way.
Clearly, when you want to build a common grid using different data sources, the first thing that you need to choose is the right scale of the grid. How do you do that? Well, it depends, of course, on the problem that you are interested in. But this is a very important choice because clearly the mechanisms that are vital to some spatial process at one scale are maybe unimportant or uninformative at another scale. The second thing that you need to do is then to find actually a way to move from one spatial scale to another. And this problem is a very well-known problem in statistics, and it's called the change of support or spatial scale. Where the support is actually the size or the volume of the data associated to a data value. Imagine, for example, that you have some data aggregated over a coarse grid, for example, here in the top, and you want to apply a transformation to this data to bring them to a grid with a much finer grid size, like the one on the bottom. The way you can do that is by, for example, applying some statistical downscaling if you're going from coarse to fine, or upscaling if you go the other way around. And with these models, basically, if you have at hand some point level data like the pins there that can drive the model, you can achieve this disaggregation and aggregation.
So what you can see now in this example here, it's in fact one of the first iterations of this common grid in which we have already projected data from the census, data from the visitors to the place coming from telco, in this case Vodafone Analytics, data from credit card transactions, and also data from the number of vehicles, so the road traffic. So as you see, all using the same sort of reference in the geometry. This grid, the applications of this grid are many. We have started already to work in some use cases. For example, site planning in retail, so where to open or where to close a retail store. For investment analysis in real estate, so where to buy or where to start constructing a building, and then in the public sector also for urban planning. So why we don't put all this into practice here? What we're going to do now is two examples, two different exercises in which we're going to use endogenous data from a retailer, this being data from its own business, so data that they will put into CARTO, for example. And this is the store locations and also the revenue per store. And then we're going to use also a multiple set of location data streams coming from different sources. So we'll use demographics, human mobility, points of interest, financial, and road traffic data that, as you've seen, we have already projected in this grid. And then we'll try to showcase what can you do and why this is important and useful. So the first exercise that we are going to do is to fuse all these multiple data streams to look for similar locations between Madrid and Barcelona.
So clearly, when you want to find similar locations between an origin location, for example, in Madrid, and different target locations, for example, in Barcelona, what you want to do is to compute some distances between the value of each of the variable that you are interested in at the origin location and the value of that variable at all target locations. And this is what you see here. If you then sum over all these differences, what you get is an overall distance. And then what you can do is to rank these distances in order of increasing distance and, for example, select the first 10 as the most similar locations or the twin areas, as we're calling this model. Everything seems fine and easy, but actually there are some few drawbacks that you have to account for when doing that. For example, we know that the range of values spanned by the number of visitors from GPS data is much larger than the range of values spanned, for example, by the number of food stores. And we don't want to give more weight to the number of visitors than the number of food stores in the computation of the distance. So we need to standardize our variables. Then we have to consider the fact that some of these variables might be correlated within each other. And this is a problem because if we are not taking out this correlation, it means that we are including in this computation of the distance some redundant information. And then there might be some missing data. So how do you compute the distance between something that exists and something that you don't have it? Because it has been anonymized, for example, because of all these anonymization procedures that we have discussed before. Even if you account for all these problems or challenges, then you come up with a distance, but how do you know that this distance is actually small enough? Or in other words, how can we define similarities? We've done all of that and come up with a similarity score that goes between 0 and 1, 1 meaning best match, or zero distance, and 0 meaning that a target location is no more similar to the origin location than the mean. So what you're going to see next are maps of this similarity score to characterize the most similar locations. First, we're going to start by selecting as the origin the location of a store in Calle Goya in Madrid. This is a location in the city center. And before applying the similarity analysis, what we can do is to get an idea of how this location positions itself in the Madrid area in terms of the different variables that we're using for the analysis. For that, we can, for example, plot the distributions of some of these variables in Madrid. You have here the population, the household income, the number of visitors, and the number of transactions. And then overlay the value of these variables at that origin location, here the vertical line. So what you see here, and as you expect, if you know Madrid, in this location, the number of visitors is much larger than what you typically get in Madrid. This is a commercial area. In fact, also the number of transactions has the same behavior. It's also a residential area, and typically wealthy people live there. And in fact, the household income is larger than the average. What you're going to see next are maps of the similarity score for similar locations in Barcelona, where we're going to start only using demographics data and then progressively adding new variables from the sources that we've mentioned before to see how the results change. So what you see here is a map of the similarity score for Barcelona. The brighter means the higher the similarity score, which means these locations are more similar to our origin location. Here we are only using population, household spending, and income data. And what you see here is that the model selects areas both in the city center and more residential area in the upper diagonal, which is notably a wealthy area. We can then add mobile data and see how the results change. And we can see that the most similar area starts shifting toward the center of Barcelona. We can keep adding new variables. Here we're adding traffic data, the number of vehicles in the road. And then adding also financial data. And then finally, we can add the data from a point of interest and see that how the model predicts as the most similar area locations right in the city center of Barcelona, in the Eixample. And if you've been in both cities, you know that this is a very sensible thing to predict. We can also change the origin location, selecting, for example, a store in Calle Embajadores, which is notably a very different area than Goya. In fact, it's a residential area where the household income is typical of Madrid and has much less visitors and transactions than the location in Goya. And we can look for similar areas in Barcelona. And what we get as the results, is this. We can see that the locations that are selected by the model are mainly residential areas, and the city center of Barcelona is excluded from the results. We can also do it in reverse by selecting a location in Barcelona. Here I'm using a store in La Rambla, and then looking for the most similar locations in Madrid. La Rambla is a very trafficked area. In fact, the number of visitors is way larger than in any area in Barcelona. It's also a commercial area with a large number of transactions, and it's a residential area where typically the household income is lower than the average. And if we look at the results in Madrid, we can see that the model selects as the most similar location, locations in the very city center of Madrid, which again, it's very sensible.
So this, if we try to think on a use case and we take the retailer one, this is very powerful if a retailer wants to look for similar areas to its known top performance in places where that retailer still doesn't have a presence. So what we are moving on to the second exercise, so the second example. So now what we are going to do is to try to correlate the business performance with the information, with the spatial patterns that we see in these different location data streams. So to do that, So to do that, what we are going to use is these two different sets of stores in which we have modeled and aggregated the revenue on a period of 6 months. And And what we're going to do is, in iterations, we're going to be selecting each of the stores in Madrid. We are going to compute the twin areas in Barcelona, and then we are going to select the stores that are in Barcelona that intersect with the twin areas above a certain threshold in the similarity score. And this we have used 0.5. Then we are going to compute the difference between the revenue of the origin store in Madrid with the stores in Barcelona that result from the previous steps. And we are going to do, as I said, this for all the different stores in Madrid. And at the end, we're going to plot the distribution of the difference between the origin store in Madrid and the stores that result from the exercise in Barcelona.
So if we do that and we plot it, what we get is this, which is the distribution of the differences between the revenues between the origin location in Madrid and the target location in Barcelona for different choices of the variables. So again, here we're starting only using demographics and then progressively adding variables until having demographics, mobility, traffic data, financial, and point of interest data. And what you see here is that as we add more variables, the distribution of the differences shift towards zero. And this basically means that as we add more variables, we are selecting increasingly more similar stores in the target area to the revenue that have revenues more similar to the revenue in the origin. And basically, in other words, what we are saying is that by adding more variables, more data, we are making the results more consistent in terms also of business performance, despite the fact that we actually didn't use the revenue data in our model.
So this, going back into a practical case, this means that we can use these multiple data streams as proxy to predict how a business, how a store will behave in a place where still it doesn't exist. So concluding with the presentation and as key takeaways, I want to highlight first the availability. So there are now many types of location data streams that can complement census data and then provide us a more updated, a more fresh view of what's happening on the territory. Second, the fact that combining all those together because of their different characteristics brings some challenges, and for this challenge you will require some geospatial thinking and some expertise, and here we hope you can come to CARTO and we can help you. And then that when you manage and you tackle these challenges and you are able to uncover the spatial patterns between location data and your business performance, you are in a position to be able to take more informed, more optimal business decisions. So, thanks. With this, we conclude our presentation.